my great pleasure to be here with you and discuss with you a bit about the recent sort of amazing sort of speed that generative models and so on have been taking. And I believe that we are at a turning point in the way that we will create, we will modify, and also analyze visual content in the future. I guess that this will have profound implications on all sorts of different application areas, on all different research areas, an industry in our society, everything that's essentially involved with images and content that you can create. And revolutions are sometimes tricky to spot when you're right at the onset of them because of the exponential growth slowly but steadily kicking in. So let's together see where we are when it comes down to how computers in the future can support us in the way that we can actually deal with visual content or content on a more general scale. So for that, let's please consider this humble cursor here. Just imagine the great power that this humble cursor here can actually have. You might say it's just a cursor, right? But when you tie it up with large amounts of data and with machine learning, you can actually turn it into this here. Your personal interface to everything that's out there, that's everything that's existing in the digital world, allows you to search and filter everything that's out there and becomes your personal interface to what's there. But you can only get what has already been created. Now imagine the infinitely greater potential that you would have if this cursor would allow you to create things which are not existent. Not search just through things which are existing, but find things that haven't been created yet. Allows you to create these things without requiring any artistic, even without any computational skills, and ideally also without requiring massive computational resources. Then you could turn this humble cursor here into this here, a system where you just type in what you want to see, what's not existing anymore, and you can take images and modify the content of those images, just verbally or with very little interaction, or even take video data, alter the visual data on the video data on the spot. Examples that you've seen here have been powered by Stable Diffusion that Sabine just mentioned, where you can essentially type in what you want to see, a sunset over a mountain range, please make it all on canvas, or turn it into a vector image, and the system then will do it. But it has plenty of more applications. I mean, here are just a few examples from our original publication, but there's been, I don't know, hundreds of more that other creative minds, much more creative minds have put together. You can utilize it, for instance, for in-painting tasks, for increasing the resolution or denoising image material, or beautifying your children's sketchy renderings there, if that's more beautiful to your taste. Now, imagine what you're seeing here would require not the servers of some big tech company. They would run on your very own hardware. Ideally, maybe even hardware that you can take with you, your mobile phone, and that of millions of other people. You can imagine how much that would democratize our access and our abilities to handle visual content, to modify visual content, and create new visual content and express yourself visually. Key for that was to make this interaction as simple as simply typing in, I want to see this and that. At the same time, also rendering it very powerful, creating beautiful images. But more importantly for me was to make it accessible. And with that, I mean, not just that what you see here is published as open source, which we did, but at the same time, our goal right from the bat was to make sure that it runs on consumer hardware, not some big tech company's compute server. Ordinary hardware that you can get for 300, 400 bucks these days, it's even scaled down to just a mobile phone. You set up saying like 10 gigabytes of VRAM should do it. And what is the challenge from a machine learning, from a computer vision perspective? The challenge is that when you want to understand our entire world out there, be able to create images of the entire world, you evidently need to see the world, need to see billions of images to understand what's out there in the last corner of this world. Now, on one end, you have billions of images, hundreds of terabytes of training data. On the other end, you have your humble $300 graphics card or even your mobile phone. How can you abstract the essence out of billions of images, hundreds of terabytes of training data, and make it fit into a mobile phone with 2 gigabytes of VRAM? How can you take literally the internet out there and make it fit into your pocket? Abstract away the essence of reality, or at least the reality that is depicted out there in this data set. That is the challenge that we've been facing when we set up with this game. Now, before I get into that, very briefly, my group is interested in several aspects of this problem. The first one that I've listed here is deep metric and representation learning. All these aspects of how we can actually achieve generalization, ideally even out of domain generalization, and learn powerful representations that generalize. I believe that it's also very important for lots of application areas that we are able to interpret these AI algorithms, or at least give users an idea how these models actually work and explain these models, and even more so, explain where they're not working or where they're abstracting things away. Self-supervision recently has gotten ever more powerful and is driving a lot of generative AI, and learning from unannotated data is there very important. But lastly, and this is what this talk will mostly focus on, will be visual synthesis, stable diffusion, and the like. Take a seat in the front row. I'm not biting. So, visual synthesis. How can we make images great or great again in the computer? I mean, you just need to look out of the window. The visual world is just beautiful. It's rich in structure. It's rich in structure on a local level. Yeah, lots of interesting textures being out there, but even more so on a global level. There's a lot of interaction between different objects in the scene. There's object consistencies that you need to model to make the image look realistic. You need to have consistent illumination between different parts of the scene and have consistent interactions between the different objects in the scene. Now, generative modeling has been around for a while, but all these approaches are facing a fundamental dilemma. And that is a trade-off between quality. Sure, we want to have beautiful images, right? You want to have great quality. And on the other end, having great data coverage. Ideally, you want to be able to speak, or in that case, render everything that is out there, not just a single object. Getting both of these together is a true challenge. We have classical examples on either end. Generative adversarial networks, for instance, great quality, super fast, but they home in typically on just a single mode. You get mode collapse. Other end of the spectrum, I really like variational autoencoders. Great coverage of the data space, but you probably know that images typically tend to get more blurry because of this great coverage that you have, and you're just having an approximation to the data likelihood. Now, recently, autoregressive models, or even more recently, diffusion models, have shown us that there's a way to tie both ends together to get this trade-off essentially mastered. And diffusion models, for me in particular, stick out as being score-based models, having here the differential of the data likelihood that they're based on. And with that comes that we finally don't need any fancy normalizations in our architecture anymore, like we had, for instance, with invertible neural networks, with the affine coupling layers and so on. And that allows essentially to utilize arbitrary architectures underneath this transformer approach. Generative adversarial networks, we ourselves in predecessor work have been using autoregressive transformers or this humble UNet architecture. Diffusion models these days deliver outstanding performance, and I guess it's fair to say that the state of the art in image synthesis is typically is currently dominated by diffusion models, lots of approaches out there. But more importantly for me, we finally got rid of this pretty much unstable minimax optimization that we used to have in adversarial learning. We finally have access to a latent variable, which allows us to efficiently edit the samples that we have to modify them post hoc. And we have the ability to have a convolutional backbone, which allows us to finally scale to high resolution images and do super resolution and the like, high resolutions that you can do with the quadratic complexity of autoregressive models. Downside still is that we have a long Markov chain, and with that comes quite some complexity. What do you mean with that? If we look very briefly, for those that haven't seen it, into how training of such a diffusion model works, you start with your little dog here, and you apply noise to that dog, just a tiny bit, so little that you would not be able to see the difference between the original dog and the dog with a tiny bit of more noise on top of it. But if you do this hundreds or even thousands of times, you end up with what you have here on your right-hand side, an image which looks like you plucked the cable from your TV set, just pure noise. Now, why would we remove content from that image? Well, computer scientists to turn that process around, right? To have a training signal for then training a neural network and essentially have a noisy image and try to reconstruct the little bit less noisy signal out of that. For that, you can utilize arbitrary different architectures that I showed you beforehand. Here, for instance, such a UNet architecture. And then the model learns to reconstruct a tiny bit less noisy image. That should be doable, right? I mean, there's just a tiny bit of noise that you added, getting rid of that should work. The magic, so to speak, happens when you do that hundreds of times after another. Then you start on your far right with just pure noise, and you repeat this over and over again in tiny steps, which add up, and you end up with something on your left, something which is not identical to this dog, but close by, a realistic rendering of what we're seeing there. The key to that is to having the same denoising autoencoder structure here for all different noise levels, as acting here as a resolution, a regularization. And what you, at the end of the day, then have learned is a hierarchy of different representations, not a spatial hierarchy like we've been doing in progressive growing of guns and similar architectures. We learn to represent images on different spatial scales, more blurry and then less blurry versions. No, all of these images have the same number of pixels, the same number, the same level of pixels and features there, but they're differing in the amount of semantic details that they contain with respect to, or that they have retained with respect to your original image here on the left. They abstract it further and further away. And isn't that what we've been all the time looking for, right? Semantic hierarchies, rather than just like blurring, which good old Gaussian pyramids could already do. And that's what you see here as an example. Now, the strength of these strong likelihood models that we've seen here is also kind of a limiting factor for them. What do I mean with that? These models try to home in every tiny bit of our data likelihood there and get the tiniest of humps, which you see there at top right, represented. They try to cover all the individual modes. Now, if you look at a rate distortion curve, that means that most of the bits at the end of the day will be allotted here to imperceptible details, things that you and I would not care about, which I cannot even sense between these three faces there on the right. And comparably few bits will be allotted to what you see here in green on your left, differences between gender, whether the person is wearing glasses, length of hair, and so on. That the model allots very few bits to, because the model is now so occupied with all of these individual pixels and covering them. Now, how can we get more bits into encoding those semantics? The evident brute force solution is scaling things up, right? With that, you're pushing this rate distortion curve towards your top right. And that has been done. Scaling up by simply making the models larger increases also the demand for compute. And you see examples like DALI work having 12 billion parameters. I know in times of GPT-4 that sounds like humble, but it's quite something, right? And there's another side to that. If you really look like what the data distribution in reality looks like, if you're in the IKEA world, you're happy. You're scaling things up and you will see your Billy shelf or whatever else 100 of times. But if you want to find or speak about, have your model understand rare instances like Da Vinci's rendering here and so on, that's occurring just once. Simply scaling up the model, you will not have enough training, sufficient training data for what you see here in your long-tailed distributions. So scaling up cannot be our only way out. Secondly, you have enormous costs in terms of compute, not just dollars, but CO2 footprint and so on. And essentially all the approaches out there, DALI and Imagine and so on, require really server hardware, not just for training, but for inference, for running those models. For me, most concerning was that means that only few players out there in the world would have the necessary resources, again, not just for training, but for applying them later on, and that limits the access there, and especially also for research. Now, spin that forward and assume a world where just a few companies would only be able to do research in this particular domain, which I could consider important for our societies, or at least having an important impact on our societies. And it's great if a company has like "Don't be evil" as their motto, but what if that changes or this research happens then somewhere else on the planet? So less diversity, creativity, and so on. And with that, evidently, our goal was to democratize the research on visual synthesis here by rendering smaller models more powerful. How can we do that? Well, we observed that powerful likelihood models are really expressive, and expressive when it comes down to long-range context, that's helpful. But when it comes down to modeling local details, they're super costly. And there are better architectures for that. For instance, our humble convolutional networks. They come with an inductive bias, or receptive field, that makes them very powerful when modeling everything that's local. Not so great for long-range interactions. You can do that by stacking them on top of another, but the interaction becomes then fairly bad. So the idea was combining the strength of both approaches. The powerful likelihood models for long-range interactions, convolutional architectures for having efficient local modeling. And that led to a two-stage approach. Now, we take the image, we have our generative model layer, starting from noise, we want to render the image here, but rather than doing that in one step, we rather have another convolutional stage in between that learns a latent representation that compresses all these, perceptually compresses the data, and gets all of these individual details that you and I would not care about, like how an individual hair of this dog is standing there, we don't really care about. We just care about the color of the hair, the length of that hair, and whatever else there, but not how individual hairs stand. We want to have a stochastic approach that's able to sample that later on. We want the overall dog to have the right shape and so on, but not like care about the individual hairs on its skin there. And then have the second stage model, the generative model, learn the interactions, the long-range interactions between all of the individual parts there of that dog. What now seems to many probably pretty much straightforward was when we started with that, not fully clear, right? I mean, you have likelihood models, powerful likelihood models, which you understand that they in the pixel domain can learn long-range interactions and deal with the complex structure of our world. But just imagine you want to now compress the local details and then have interactions between parts of a feature space. How would that work together? So how do you train, first of all, this perceptual compressor there? And that is where predecessor work of us kicked in, the VQ-GAN approach or taming transformer approach, where we take the pixel image, run it through an encoder into some latent space. Here it was vector quantized representation. In the diffusion model, this is a continuous representation. And then run it back through a CNN decoder into the image space. You train it, in contrast to those who know VQ-VAE, not by having a L2, L1 reconstruction loss, but by having a perceptual loss. And in addition to that, adding a patchwise discriminator that favors realism over just a picture-perfect reconstruction. If you do that, you can attain a very compact representation that gets rid of all of those details that we wouldn't care about anyhow, and have the powerful likelihood model, first of all, here in the VQ-GAN approach, being a transformer approach, concentrate on what it's great at, long-range interactions. So in VQ-GAN, it was an autoregressive approach, which takes the individual parts and learns interaction from one to the others. Then this leads to what you're seeing here. The results here of the VQ-GAN on the far right being significantly crisper than the VAE type approach that DALI used. DALI came out like 2 weeks or so after, only after our VQ-GAN approach, and still you see the results being here significantly crisper that you have by VQ-VAE, which you also see in the FID numbers that you have here on bottom right. But most importantly, the results weren't just like crisper, but we have also a significantly higher compression. Yeah, this year and this year, if you compare the numbers, being 4 times higher compression rate, which means for a transformer with quadratic complexity is 16 times computational gain over the other approach when the results were still crisper. So you see that this perceptual compression quite a bit helps in that case to improve things. In latent diffusion models, or stable diffusion as it's called, you now have the diffusion process here at the top, which takes your representation and adds noise to it in tiny steps. And then we turn that process around by means of this denoising unit in a lot of individual steps. And do this, however, not in the pixel space, but in the second space, in this latent space, in the second stage representation. Now you can add to this denoising process an arbitrary conditioning here in terms of text, for instance, as site information, or any other sort of site information that you consider, semantic segmentation, another image, and have cross-attention layers inject this site information into the denoising process. And then you guide, by means of your text, how this denoising process should work. So essentially cross-attention layers modulating the denoising in the unit. And with that approach, you can do this. You type in, I want to have a photograph of a mountain, tree, lake, highly detailed, photorealistic. Wait 5-10 seconds, and out comes a megapixel image like this one here. Just like that, without any computational skills, artistic skills, just typing these few words in. And the approach not just creates this, you can create dozens, hundreds of images which fit this text description up there. But not only that, this generic conditioning allows you not just to condition on text, but also to condition on a layout, which you're seeing here. Now saying like, I want to have trees there and sky there and so on. To do super resolution, start with a low res image and have the approach render then the higher resolution images, complete an image and hallucinate what you're not seeing there, or take, which you also see at bottom right, a depth mask and turn that into a 3D rendering of a scene. The approach you can utilize for in-painting, you take a scene and ask what's behind that tree here and hallucinate essentially one or many renderings of what's behind there and achieve state-of-the-art performance in painting, although it's not a dedicated in-painting approach. You just utilize this visual foundation model for this particular task. But what recently people apparently get most interested in were like these text guided image to image, not text to image, but image to image with text guidance, where we relied on the interesting SD-edit approach, which I recommend you check out, where you take essentially an image that you start with, diffuse it a bit, add a bit noise, and then go for the backwards pass where you inject the content that you want. And with that, you can do lousy renderings like I can do. Yeah, and then say this should have been Munich Frauenkirche rooftops, buildings, and make it Claude Monet or then go, and the system then renders that according to your visual input, and this text prompt creates that. Now, here are a few tips and tricks for those of you who are working with diffusion models. For us, it turned out to be very important to utilize classifier-free guidance as a guiding signal for the diffusion process. We essentially take this conditioning signal, which you have here, and in 10, 15, 20% the cases you drop it. So Hohenzollern's here have really had a super interesting, super simple to use approach, which I can only recommend to use whenever you have a conditioning signal there, dropping it every now and then. That helps as a regularization. Secondly, we worked with different text encodings, and Google in their work, which you see cited down here, have shown or have evaluated also different text encoders, and while T5XXL and other big approaches definitely have an edge, you see here that Clip gives you a nice trade-off in terms of like size and performance. And since we wanted to run things on consumer hardware, we then decided for Clip, which for us got us reasonably close in terms of performance. But lastly, and most importantly, don't throw all the data at once in there. You need to do it like with students. You need to start easy and then get more and more complicated. So we started with smaller sets of data out of the line 2B data set with just half the resolution, 256 squared, and then went to 512 squared, and in smaller and smaller batches added additional data. This is, for those that are interesting, where stability came in and simply gave us sponsoring for AWS credit, where we then computed it. But the approach, which you see published in CVPR, happened before that. And with that, well, the rest is history, as they so tell. Stable Diffusion was out, and here you see current GitHub projects after start, and towards your left here, these are GitHub stars of Stable Diffusion. I'm just showing this to highlight the many creative minds that are now building something on top of that, improving it further. I see there's a bit like an open platform like Linux and whatever else. I find now interesting what others are doing based on our system in such a short amount of time. And I guess it's fair to say that there's been a Cambrian explosion, I read it somewhere on the internet, in terms of creative tools and also research based on the system. So there's a search engine dedicated to Stable Diffusion created images. If you're interested in like how these prompts look like, you can grasp them. This search engine doesn't show you just images, but also the prompts and everything that you need to create it. There's plugins for Photoshop, so you don't need to start with an empty canvas, but you can just type something in and then do your typical Photoshop or GIMP Blender thing. There's been tons of creative artists that did interesting things based on Stable Diffusion and rendered images, rendered videos. I'm sure you've seen plenty there, and no need to go through all of the beautiful renderings that are out there. And there are fun, quite a number of fun research projects based on Stable Diffusion. I just want to here highlight one or two. And this is something that popped up recently. I'm not recommending that this is the best way to deal with audio, but what they've done is just take Stable Diffusion out of the box, yeah, and essentially you take spectrograms, you take audio, you turn that into a spectrogram, and then show the spectrogram to Stable Diffusion and say like, hey, I mean, that's an image, right? Take this image and re-render that and change the text prompt there a bit to alter the content. And with that, essentially create a music generator that outputs a spectrogram, which you can turn back into audio. And in that case, funk bass line, jazzy saxophone. Sounds somewhat funky, right? You can then do latent space interpolation in the Stable Diffusion space. And just highlighting this because Stable Diffusion wasn't touched. I mean, we never kind of thought of audio. You just heard this insert tells you about generalization performance of this approach. And recently, I've seen a paper doing cryo-EM based on Stable Diffusion for those of you interested in there. So it seems like it's a fairly broad foundation model. So let me wrap up here. We've seen that we can combine the efficiency of convolutions with the expressiveness of powerful diffusion models or autoregressive models for the long-range context, and that leads to efficiency. that helps to democratize the access to this powerful tool and allows to do high-res image synthesis in a feasible manner. We have a generic conditioning algorithm in there, which made it open for so many applications, which you've just seen. And there's definitely a lot to explore in future research. To see a few examples, improving latent space autoencoder, which we have never touched. And this is just what we had beforehand. Worked fairly well for us, but there's a lot to improve there. Larger language models, you will lose the access to consumer hardware, but that's definitely something to consider, or increasing the number of parameters. But so far, I've shown you how we can take these likelihood models and learn representations more efficiently. Now I want to switch gears and ask what we should at all learn with such a model. What do I mean with that? Well, if you look at artists, like gifted artists like Monet, when they were painting trees, he went out in the wild and looked at trees. Now, you can, like Ronald Reagan so infamously said, say, how many more trees do you need to look at? Yeah, a tree's a tree. But evidently, nature gives you an infinite amount of variability. And there was a reason why he looked out there. Contrast this to how we deal with our neural networks. We take all the data that we have there and simply stuff that into these costly parameters of a neural network and store it all in there, rather than having them on the fly look when they're doing the rendering at the trees. We store them in there. So I'm advocating here for an approach that tries not to represent all the local detail in a generative model, but what instead? Well, instead, take a database of patch examples and look up the relevant patches for the particular inference task at hand from this database. So in our case, we took a database of a few million patch images here, 20 million patches extracted there. And whenever you want to render an image, we are then having the likelihood model focus on a meaningful composition rather than the individual patches or the individual details. So the details it gets from the database, and it can focus on learning the interactions. How does that work? We're looking here at a semi-parametric approach. So what you see here is the standard pipeline of a likelihood model. When you train it, we start with the image. In green box is the likelihood model, and you want to reconstruct that image. So far, so good. But now we add conditioning information here. We condition this likelihood model on nearest neighbors, which we get here from this database, which you see up here. And I guess we can all imagine that if you want to reconstruct this bird here, and these here are your nearest neighbors, that they are quite helpful and make your task of rendering this bird much easier, right? And that's what we're doing here. Not directly the patches. We're taking actually fixed encoding of those patches, but I guess that's details here. During inference, you can then take this database, retrieve patches from this database, and with that power the diffusion process or your autoregressive process. And it's important for me to stress that you don't need access to the training data. This database is and can be a separate database, separate from your training set. So separate that you can even swap it during the inference stage. More on that on the next slide. And just a brief take-home message here. It turns out that the semi-parametric approach provides most gain when we're transferring to test tasks which are vastly different from the training task. Kind of makes sense, right? In that case, getting from the test data additional samples which you did not have available during training definitely helps. Now, here's an interesting catch. If we train this model on photos from ImageNet, and then during testing, swap the database to some art database, WikiArt. This model has never been trained on style transfer, but you see that this model in a zero-shot manner now, because the nearest neighbor is not coming from ImageNet anymore, but from this WikiArt database, starts to stylize images. So you can see how you can do domain transfer by simply swapping the database. No training, no fine-tuning, nothing. You just take the model out of the box and simply swap the patch database that you have there. And, well, semi-parametric approach, you may wonder, isn't that making life more complicated? Actually, no. Here you see model parameters and the performance that we achieve, and you see that we're pretty much on par with having much fewer parameters. That retrieving from a database eventually significantly reduces the necessary model size that we actually need. And since nearest neighbor lookup, thanks to Google, scan library works super fast, 100 milliseconds for these 20 million patches, negligible time, our approach is actually 10 times faster than the other approaches that are not here semi-par or non-parametric. So in summary, my argumentation here would be don't learn all of these local details in these likelihood models, have these powerful models rather concentrate on the combination of those patches. That leads to smaller models. It improves the performance of those models by having the models do what they're great at, learning compositions rather than local details. And it also makes it possible, like we've seen in the last example, to have a convenient post hoc transfer of the model to enter any new tasks by simply swapping the database. And with that, I want to, before closing, look at a last topic, which I here call looking at the dark matter of neural networks. What do I mean with that? Neural networks are great in learning structure from data, but it's equally important what they're not learning, what they're learning to ignore. And I want to learn at this dark matter, things that such a neural network, when processing the snow leopard and learning a latent representation, FC7 or whatever, what this representation here has ignored. I guess we can all imagine then on the way from the front to the back, a lot of information has to go away. At the end of the day, there's just one class label, snow leopard. All the different snow leopards will receive the same label. So it's clear that as you go down here, this train, there will more and more information be lost. Can we analyze the information that is lost? And can we potentially recover it? And you see this problem when you turn that process around, take FC7, want to reconstruct, you get this here. Just one example on the manifold of all possible realizations. This has profound implications. For those that do medical imaging, CT imaging, you typically want to do as a low dose to save your patient. You do fluorescent imaging. You typically want to do this at a low dose to avoid photo bleach. The images that you get out there are evidently much lower quality than the high dose examples if you were able to do that. That's why all of these devices typically come with image enhancement algorithms. I know quite a few of you have been working on exactly those. I guess it's apparent that the output of those algorithms is not identical to the high dose image. They're getting close. Our field has done great work in denoising, removing the blur, increasing the resolution, and so on. But the question that I like to pose is, what are the biases of these enhancement algorithms? They need to take tiny bit of structure, low-res images, and hallucinate essentially all the information that is lost. We can imagine that this is a one-to-many mapping, lots of different potential outputs. Which one do they choose? What structures do they ignore in that process? What structures do they invent, which are not there? I guess when you're a radiologist, you can imagine like you don't want structures to be invented, which are not there in the patient. So let's look how to do that. How can we recover the invariances that this model here has established in some latent representation Z, which you see here in orange? For that, let's take an encoder-decoder architecture, which you can ramp up at least around this spot Z so that it's epsilon approximate. You can all the bits in there to get this thing clear. And then it's clear that at the top, we're having much less information than at the bottom. Yeah, essentially at the bottom, we have a perfect reconstruction of this sample. At the top, there's a lot of information lost. There's an information mismatch. How can I map from between top and bottom and essentially recover the information which is missing at the top? Normalizing flows to the rescue. Normalizing flows, for those who haven't seen it, you take a humble Gaussian distribution, and by means of a lot of bijective steps, you map that over to a complex distribution of your data set. Because it's bijective, you can go back and forth between both. And you're guaranteed that you're not inventing additional structures there besides what you have already seen in your training data. So you can go both ways. Now we take such an INN, or rather a conditional invertible neural network, which maps between Z at the top and this perfect reconstruction at the bottom. Essentially, we condition on what we have, and we are lacking information, additional information, right?
This is all the information the invariant information that is lost here. If we take this here and add this invariant representation, we get this here. So essentially, we've now learned a conditional bijective mapping between the invariant information, the information that we're missing, and the full representation conditioned on what we have observed. Yeah? And with that, we can now take, for instance, this perfect reconstruction, condition on what we have observed, and ask, what have we been missing? Yeah, so you can, because it's bijective, turn this around. I have observed this here. This is what it should be. What is the difference, so to speak, between these two? And reconstruct that. And that is the difference. All of these snow leopards here at the bottom will look exactly identical to this neural network out there. It won't notice if a snow leopard sticks the tongue out at you, for instance, in that particular case. And you can do that on different levels on your neural networks. And as you would imagine, at the front of the neural network, it will be more detail preserving if you're going to the end, evidently more and more invariances. And we can now do that on our CT imaging, take a low dose image and now answer, like, what are the biases, what structures has this model ignored and which ones has it reinvented, and take this conditional INN and essentially learn in the low dose space which images here look identical to this model that you have up here. And this is what comes out. And you see here indicated with a blue arrow that there are quite a few structures which just miraculously pop up. And the model would not be able to distinguish between what you have here, any of these, and this input image here. You can imagine, like, if this would be, I don't know, whatever lesion that you have there, radiologist being quite interested in this thing not being noticed, being there, or this thing being invented, being there, although it's in truth not there. And understanding what the image enhancement algorithm in that case is blind to, or just inventing, hallucinating, is evidently important. You can do that on different layers of your neural architecture for a reconstruction, and with that get a better understanding there. Now with that, I'd like, in the interest of time, to come to a close. We've started off seeing how we can make powerful generative models these days more efficient by combining the inductive biases, the receptive fields of convolutional architectures, with a powerful ability to learn long-range interactions in likelihood models, especially diffusion models. And with that, boost them to architectures which run on arbitrary consumer hardware. We've seen that we can go further by means of retrieval augmentation. And essentially, this results in smaller likelihood models with improved performance by having them focus on what they're great at, learning compositions, and not learning the local data. This also gives us convenient post hoc transfer without training or fine-tuning, taking a model by simply swapping the database and adjusting it to novel data. And lastly, we've been looking a bit into explainable AI and understanding the invariances of models. So essentially taking conditional invertible neural networks to efficiently translate between a representation that has these invariances and a full representation to recover the difference between these two and recover the invariances and explaining the invariances that the model has learned. With that, let me thank you for your attention and thank my wonderful team that made all of this work possible.